What specific problem does the feasible learning Florida framework address that traditional empirical risk minimization does not? How does this distinction affect model generalization and performance?
The feasible learning Florida framework addresses the limitation of traditional empirical risk minimization in that it focuses on ensuring satisfactory performance across all training samples rather than optimizing for average performance. While seeks solutions that achieve zero training loss, Florida imposes a bounded loss constraint for each individual training sample, allowing for non-interpolating solutions that can potentially enhance model generalization. This distinction leads to a more concentrated loss distribution, resulting in fewer instances of excessively high losses, which is particularly beneficial in applications requiring consistent performance across all data points. Additionally, FL's approach introduces functional regularization, preventing overfitting by not demanding excessive minimization of the loss beyond a specified threshold. Consequently, Florida can achieve comparable average performance to while offering improved robustness and uncertainty quantification, making it a compelling alternative in scenarios where individual sample performance is critical.
How does the proposed method of feasible learning Florida work? Illustrate the algorithmic steps and theoretical underpinnings used to achieve the loss constraint for each training sample.
Feasible learning Florida operates by framing the learning task as a feasibility problem, where the goal is to find a predictor that meets a specified loss constraint for each training sample. The optimization problem is defined with a constant objective function while imposing a constraint on the loss for each sample, denoted as G_I bold symbol theta lec epsilon, where epsilon is the maximum allowed loss. The algorithm employs a primal-dual optimization approach, utilizing Lagrangian duality to manage the constraints, where each sample's loss is weighted by a corresponding Lagrange multiplier that adjusts dynamically based on the difficulty of fitting that sample. The primal updates follow the gradients of the per-sample losses, while the dual updates involve projected gradient ascent on the multipliers, ensuring that samples with high losses receive more focus during optimization. This method allows Florida to achieve a more concentrated loss distribution across samples, promoting consistent performance and reducing the impact of outliers compared to traditional empirical risk minimization
Can you provide a detailed example that illustrates the inner workings of the feasible learning Florida algorithm? Walk through the algorithm steps using a hypothetical dataset and explain how the constraints are enforced during training.
To illustrate the inner workings of the feasible learning Florida algorithm, consider a hypothetical dataset with 3 samples: bold symbol x_1, bold symbol y_1, bold symbol x_2, bold symbol y_2, and bold symbol x_3, bold symbol y_3. The Florida framework formulates an optimization problem with a constant objective function while enforcing a loss constraint for each sample, denoted as G_I bold symbol theta lec epsilon, where epsilon is the maximum allowed per sample loss. For instance, if we set epsilon equals 0.5, the model must ensure that the loss for each sample does not exceed this threshold. During training, the algorithm initializes Lagrange multipliers, bold symbol lambda_0 equals bold symbol 0, and performs alternating updates. In the primal update, the algorithm computes the gradients of the per-sample losses, G_I bold symbol theta, and adjusts the model parameters, bold symbol theta, based on the weighted loss gradients, where the weights are determined by the corresponding multipliers. If a sample's loss exceeds epsilon, its multiplier increases, emphasizing its importance in subsequent updates. Conversely, if a sample's loss is below epsilon, its multiplier decreases, potentially reaching 0, which reduces its influence on the model. As training progresses, the algorithm dynamically reweights the samples based on their loss performance, effectively enforcing the constraints. For example, if bold symbol x_1 bold symbol y_1 has a loss of 0.6, its multiplier will increase, prompting the model to focus on reducing this loss in future iterations. This process continues until the model achieves satisfactory performance across all samples, ensuring that the constraints are met while allowing for flexibility in the optimization dynamics. Thus, Florida not only seeks to minimize the loss but also guarantees that each sample's loss remains within the specified bounds, leading to a more robust learning outcome.
What are the advantages of using feasible learning, Florida, and resilient feasible learning, RFL, over traditional in terms of sample performance and loss distribution? Provide specific metrics or qualitative aspects from the experiments that support your claims.
Feasible learning, Florida, and resilient feasible learning, RFL, offer significant advantages over traditional empirical risk minimization, by focusing on sample-centric performance and improving loss distribution. Specifically, Florida ensures satisfactory performance across all training samples, contrasting with ERM's average performance optimization, which can overlook poor performance on individual samples. In experiments, Florida demonstrated a more concentrated loss distribution, resulting in fewer instances of excessively high losses compared to as indicated by the cumulative density function, CDF, and conditional value at risk, CVAR metrics. RFL further enhances this by allowing for flexibility in constraint satisfaction, which leads to improved average and maximum performance, particularly in challenging datasets where FL's constraints may be too restrictive. For instance, in the UTK face age regression task, RFL outperformed in both average train and test errors, showcasing its robustness and effectiveness in managing loss distributions across various tasks.
How was the effectiveness of the Florida method validated in the paper? Discuss the experimental design, datasets used, and key metrics that were employed to demonstrate the performance of Florida compared to
The effectiveness of the feasible learning, Florida method was validated through empirical evaluations across various tasks, including CIFAR-10 classification, UTK face age regression, and preference alignment using direct preference optimization, DPO. The experimental design involved training models using Florida, resilient feasible learning, RFL, and traditional empirical risk minimization, under the same training budget of 200 epochs, allowing for a direct comparison of performance. Key metrics employed included average performance on training and test sets, as well as the distribution of losses, specifically focusing on the cumulative density function, CDF, and conditional value at risk, CVAR, to assess consistency and robustness across samples. Results indicated that Florida and RFL achieved comparable average performance to while demonstrating advantages in tail behavior and robustness, particularly in scenarios where FL's sample-centric nature led to fewer instances of excessively high losses. Overall, the experiments provided comprehensive evidence supporting Florida as a compelling alternative to highlighting its unique properties and performance characteristics.
What limitations did the authors identify regarding the Florida and RFL methodologies, particularly concerning constraint selection, epsilon, and the potential for infeasibility? How could these limitations impact practical applications of the proposed framework?
The authors identified that a significant limitation of the feasible learning Florida methodology is the challenge of selecting an appropriate constraint level, epsilon. If epsilon is set too tightly, the Florida problem may become infeasible, meaning no solutions exist that satisfy the constraints. Conversely, if epsilon is too loose, it may lead to vacuous constraints that fail to ensure good performance. This trade-off complicates practical applications, as the optimal choice of epsilon depends on the model data and task specifics. To address this, the authors introduced resilient feasible learning, RFL, which relaxes the constraints using slack variables, ensuring feasibility even when the original Florida problem is infeasible, thus enhancing the robustness of the framework in real-world scenarios.